The Black Hole War by Leonard Susskind, continued. Disc 4. Entropy and heat. Heat is the energy of random chaotic motion, and entropy is the amount of hidden microscopic information. Consider the tub of water, now cooled to the coldest possible temperature, absolute zero, at which point every molecule is locked into its precise location in an ice crystal. There is very little ambiguity in the location of each molecule. In fact, anyone who knows the theory of ice crystals could say exactly where each atom lies, even without a microscope. There is no hidden information. The energy, temperature, and entropy are all zero. Now, add a bit of heat by warming the ice. The molecules begin to jiggle, but only a bit. A small amount of information is lost. We lose track, if only a little, of the details. The number of configurations that we might mistakenly confuse with one another is larger than it was. Thus, a bit of heat raises the entropy, and it gets worse as more energy is added. The crystal approaches the melting point, and the molecules begin to slide right past each other. Keeping track of the details quickly becomes prohibitive. In other words, as energy increases, so does entropy. Energy and entropy are not the same thing. Energy takes many forms, but one of those forms, heat, is joined at the hip with entropy. More about the second law. The first law of thermodynamics is the law of energy conservation. You cannot create energy, you cannot destroy it. All you can do is change its form. The second law is even more discouraging. Ignorance always increases. Imagine a scene in which a diver plunges into a swimming pool from a springboard. Potential energy goes into kinetic energy, goes to heat. He quickly comes to rest, and the original potential energy is converted to a slight increase in the thermal energy, heat, of the water. With that slight increase, there is a slight increase in entropy. The diver would like to repeat the performance, but he's lazy and doesn't want to climb the ladder to the diving board again. He knows that energy can never disappear, so why not just wait until some of the heat in the pool gets converted back to potential energy, his potential energy? Nothing about the conservation of energy would prevent him from being shot up to the diving board while the pool cools a bit, the reverse of the dive. Not only would he wind up on the board, but the entropy of the pool would decrease, implying a surprising decrease in ignorance. Unfortunately, our wet friend finished only half his thermodynamics course, the first half. In the second half, he would have learned what we all know. Entropy always increases. Energy always degrades. The change of potential, kinetic, chemical, and other forms of energy into heat always favors more heat and less of those organized, non-chaotic forms of energy. This is the second law. The total entropy of the world always increases. It's for this reason that a car will screech to a halt when the brakes are applied, but applying the brakes to a stationary car will not get it moving. The random heat of the ground and the air cannot be turned into the more organized kinetic energy of a moving vehicle. It's also the reason that the heat in the sea cannot be tapped to solve the world's energy problems. On the whole, organized energy degrades to heat, not the other way around. Heat, entropy, information. What do these practical utilitarian concepts have to do with black holes and the foundations of physics? The answer is everything. In the next chapter, we will see that black holes are fundamentally reservoirs of hidden information. Indeed, they are the most densely packed information storage containers in nature, and that may be the best definition of a black hole. Let's find out how Jacob Bekenstein and Stephen Hawking came to realize this central fact. Chapter 8. Wheeler's Boys, or How Much Information Can You Stuff in a Black Hole? In 1972, while I was talking to Richard Feynman in the West End Cafe, a Princeton graduate student named Jacob Bekenstein was asking himself this question: what do heat, entropy, and information have to do with black holes? At that time, Princeton was the world's center for the study of gravitational physics. That may have had something to do with the fact that Einstein had lived there for more than 2 decades, though by 1972 he had been dead for 17 years. The Princeton professor who had inspired many brilliant young physicists to study gravity and think about black holes was John Archibald Wheeler, one of the great visionaries of modern physics. Among the many famous physicists who were profoundly influenced by Wheeler during this period were Charles Misner, Kip Thorne, Claudio Teitelbaum, and Jacob Bekenstein. Wheeler, who earlier had been Feynman's PhD advisor, was a disciple of Einstein. Like the great man himself, he believed that the key to the laws of nature lay in the theory of gravity. But unlike Einstein, Wheeler, who had worked with Niels Bohr, was also a believer in quantum mechanics. Thus, Princeton was a center of research, not only on gravity, but also on quantum gravity. At that time, the theory of gravity was a relatively unpopular backwater of theoretical physics. Elementary particle physicists were making giant strides in the reductionist march toward ever tinier structures. Atoms had long given way to nuclei, and nuclei to quarks. Neutrinos were finding their rightful role as equal partners with electrons, and new particles such as the charmed quark had been hypothesized and were within a year or two of experimental discovery. The radioactivity of nuclei was finally being mastered, and the standard model of elementary particles was about to be declared. Elementary particle physicists, myself included, thought they had better things to do than waste their time on gravity. There were exceptions, such as Steven Weinberg, but most considered the subject to be frivolous. In retrospect, this disdain for gravity was a very myopic view. Why was it that the aggressive leaders of physics, the bold frontiersmen of the subject, were so uncurious about gravity? The answer is that they could see no way that gravity could possibly have significance for the way elementary particles interact with one another. Imagine that we had a switch that allowed us to turn off the electrical force between an atomic nucleus and the electrons, thereby leaving only gravitational attraction to hold the electrons in orbit. What would happen to an atom when we flipped the switch? The atom would immediately expand, because the force that holds it together would have diminished. How big would a typical atom become? A good deal bigger than the entire observable universe. And what would happen if we left the electrical force switched on, but turned off gravity? The Earth would fly away from the Sun, but the change in an individual atom would be far too small to make any difference. Quantitatively, the gravitational force between 2 electrons in an atom is roughly 1,000,000 billion times weaker than the electrical forces. Such was the intellectual environment when John Wheeler boldly set out to explore the ocean of ignorance that separated the conventional world of elementary particles from Einstein's theory of gravity. Wheeler himself was a walking enigma. In appearance, he looked and sounded like a buttoned-down businessman. He could easily have fit into the boardrooms of the most conservative corporations in America. In fact, his politics were conservative. The Cold War was far from over, and John was a staunch anti-communist. And yet, throughout the 1960s and 1970s, in an age of unprecedented campus activism, he was deeply beloved by his students. Claudio Teitelbaum, who today is the most eminent Latin American physicist, was one of John's students. Claudio, the scion of a famous Chilean left-wing political family, was one of John's many disciples who later achieved fame. The family was politically allied with Salvador Allende. Claudio himself was a fearless, outspoken foe of the dictatorial Pinochet regime. But despite their political differences, John and Claudio have had an extraordinary friendship based on love and mutual respect for each other's opinions. The first time I met Wheeler was in 1961. I was an undergraduate at City College of New York, with a somewhat unorthodox academic record. One of my instructors, Harry Sudak, a cigar-chomping, cussing professor from the same Jewish left-wing working-class background that I came from, took me down to Princeton to meet him. The hope was that Wheeler would be impressed and that I would be admitted as a graduate student, despite my lack of an undergraduate degree. At the time, I was working as a plumber in the South Bronx, and my mother thought I should dress properly for the meeting. To my mother, that meant that I should show solidarity with my social class and dress in my work clothes. These days, my plumber in Palo Alto dresses about the same way that I do when I lecture at Stanford University. But in 1961, my plumbing costume was the same as my father's and that of all his South Bronx plumber buddies: Lil Abner bib overalls, a blue flannel work shirt, and heavy steel-toed work shoes. I also sported a watch cap to keep the dirt and grime out of my hair. When Harry picked me up for the drive to Princeton, he did a double take. The big cigar fell from his mouth, and he told me to go back upstairs and change. He said that John Wheeler was not that kind of guy. When I walked into the great professor's office, I saw what Harry meant. The only way I can describe the man who greeted me is to say that he looked Republican. What the hell was I doing in this wasp's nest of a university? 2 hours later, I was completely enthralled. John was enthusiastically describing his vision of how space and time would become a wild, jittery, foamy world of quantum fluctuations when viewed through a tremendously powerful microscope. He told me that the most profound and exciting problem of physics was to unify Einstein's two great theories, general relativity and quantum mechanics. He explained that only at the Planck distance would elementary particles reveal their true nature, and it would be all about geometry, quantum geometry. To a young aspiring physicist, the stuffy businessman exterior had morphed into an idealistic visionary. I wanted more than anything to follow this man into battle. Was John Wheeler really as much of a conservative as he appeared? I don't really know. But he was certainly not a prudish moralizer. Once, while John and my wife Anne and I were having a drink in a Valparaiso cafe on the beach, he got up to take a walk, saying he wanted to check out the South American girls in their bikinis. At the time, he was in his late 80s. In any case, I never did get to be one of Wheeler's boys. Princeton did not admit me. So I went off to Cornell, where physics was far tamer. It would be many years before I felt the same thrill I had in 1961. Sometime around 1967, Wheeler became very interested in the gravitationally collapsed objects that Karl Schwarzschild had described in 1917. At that time, they were called black stars or dark stars. But that didn't capture the essence of the objects, the fact that they are deep holes in space whose gravitational attraction is irresistible. Wheeler began calling them black holes. At first, the name was blackballed by the preeminent American physics journal Physical Review. Today, the reason seems hilarious. The term black hole was deemed obscene. But John fought it through the editorial board, and black holes they became. Amusingly, John's next coinage was the saying, "Black holes have no hair." I don't know whether Physical Review was again outraged, but the terminology stuck. Wheeler wasn't trying to provoke the journal editors. Instead, he was making a very serious point about the properties of black hole horizons. What he meant by hair was observable features, perhaps bumps or other irregularities. Wheeler was pointing out that the horizon of a black hole was as smooth and featureless as the smoothest bald pate, actually much smoother. When a black hole formed, say, by a star collapsing, the horizon very quickly settled down to a perfectly regular, featureless sphere. Apart from their mass and rotational speed, every black hole was exactly like every other. Or so it was thought. Jacob Bekenstein, an Israeli, is a small, quiet man, but his gentle, scholarly appearance belies his intellectual boldness. In 1972, he was one of Wheeler's graduate students interested in black holes, but he was not interested in these objects as astronomical bodies that might someday be seen through telescopes. Bekenstein's passion was the foundations of physics, the basic underlying principles, and he had a sense that black holes had something profound to say about the laws of nature. He was particularly interested in how black holes might fit together with the principles of quantum mechanics and thermodynamics that had so preoccupied Einstein. In fact, Bekenstein's style of doing physics was much like Einstein's. Both were masters of the thought experiment. With very little mathematics, but with a lot of deep thinking about the principles of physics and how they apply to imaginary, but possible, physical circumstances, both men were able to draw far-reaching conclusions that would profoundly affect the future of physics. Here is Bekenstein's question in a nutshell. Imagine yourself orbiting a black hole. In your possession is a container of hot gas with a good deal of entropy. You throw the container of entropy into the black hole. According to the standard wisdom, the container would simply disappear behind the horizon. For all practical purposes, that entropy would completely vanish from the observable universe. According to the prevailing view, the featureless, bald horizon couldn't possibly hide any information, so it would seem that the entropy of the world had decreased, in contradiction with the second law of thermodynamics, which says that entropy never decreases. Could it be that easy to violate so deep a principle as the second law? Einstein would have been appalled. Bekenstein concluded that the second law is too deeply rooted in the rules of physics to be so easily violated. Instead, he made a radical new proposal. Black holes themselves must have entropy. He argued that when you count up all the entropy in the universe, the missing information in stars, interstellar gas, the atmosphere of the planets, and all the bathtubs of warm water, you must include a certain amount of entropy for each black hole. Furthermore, the bigger the black hole is, the bigger its entropy. With that idea, Bekenstein could rescue the second law. Einstein would no doubt have approved. Here is how Bekenstein thought about it. Entropy always goes together with energy. Entropy has to do with the number of arrangements of something, and that something, in all cases, has energy. Even the ink on a page is made of massive atoms, which, according to Einstein, have energy, because mass is a form of energy. One might say that entropy counts the possible ways of arranging bits of energy. When Bekenstein, in his imagination, tossed a container of hot gas into a black hole, he was adding to the black hole's energy. In turn, this meant an increase in the black hole's mass and size. If, as Bekenstein guessed, black holes have entropy, which increases with their mass, there was a chance of rescuing the second law. The entropy of the black hole would increase more than enough to compensate for what was lost. Before explaining how Bekenstein guessed the formula for black hole entropy, I will explain why it was such a shocking idea. So shocking that, according to Stephen Hawking, he initially dismissed it as nonsense. You can read all about his initial skepticism in his book, A Brief History of Time. Entropy counts alternative arrangements, but arrangements of what? If a black hole horizon is as featureless as the smoothest conceivable bald head, what is there to count? According to this logic, a black hole should have zero entropy. John Wheeler's claim that black holes have no hair seemed to directly contradict Jacob Bekenstein's theory. How to reconcile teacher and student? Let me give you an example that will help you understand. The print on a page decorated with various shades of gray is really composed of tiny black and white dots. Let's suppose we have 1,000,000 black dots and 1,000,000 white dots to work with. One possible pattern would be to divide the page in half, either vertically or horizontally. We can make one half black and the other half white. There are only 4 ways to do this. Left side white, right side black, left side black, right side white, top half black, bottom half white, top half white, bottom half black. We see a strong pattern and sharp distinctions, but only a very few arrangements. Strong patterns and sharp distinctions typically mean small entropy. But now let's go to the other extreme and randomly distribute the equal number of black and white pixels over the same square. What we see is a more or less uniform gray. If the pixels are really small, the gray will look extremely uniform. There is an enormous number of ways to rearrange the black and white dots that we would not notice without a magnifying glass. In this case, we see that large entropy often goes together with a uniform, bald appearance. The combination of apparent uniformity and large entropy indicates something important. It implies that the system, whatever it is, must be made of a very large number of microscopic objects that A, are too small to see, and B, can be arranged in many ways without changing the basic appearance of the system. How Bekenstein calculated the entropy of a black hole. Bekenstein's observation that black holes must have entropy, in other words, that despite their apparent baldness they hold hidden information, is one of those simple but profound observations that, at a stroke, change the course of physics. When I began to write books for a general audience, I was strongly advised to keep the equations down to only one, E equals mc squared. I was informed that for every additional equation that I included, I would sell 10,000 fewer books. Frankly, that goes against my experience. People like to be challenged. They just don't like to be bored. So after a good deal of soul-searching, I decided to take the risk. Bekenstein's argument is one of such extraordinary simplicity and beauty that I feel not to include it in this book would be a sad dumbing down of the material. However, I have taken pains to explain the results so that the less mathematically inclined reader can safely skip over the few simple equations without losing the essence. Bekenstein didn't directly ask how many bits could be hidden inside a black hole of a given size. Instead, he asked how the size of a black hole would change if a single bit of information was dropped into it. This is similar to asking how much the water in a bathtub will rise if a single drop of water is added. Even better, how much will the water rise if a single atom is added? That raised another question: how to add a single bit. Should Bekenstein throw in a single dot printed on a scrap of paper? Obviously not. That dot is composed of a huge number of atoms, and so is the paper. There is far more information in that dot than a single bit. The best strategy would be to throw in one elementary particle. Suppose, for example, that a single photon falls into a black hole. Even one photon can carry more than a single bit of information. In particular, there is a good deal of information in knowing exactly where the photon enters the horizon. Here, Bekenstein made clever use of Heisenberg's concept of uncertainty. He argued that the location of the photon should be as uncertain as possible, provided only that it gets into the black hole. The existence of such an uncertain photon would convey only a single bit of information, namely, it's there, somewhere in the black hole. Recall from Chapter 4 that the resolving power of a light beam is no better than its wavelength. Now, in this particular case, Bekenstein did not want to resolve a spot on the horizon. He wanted it to be as fuzzy as possible. The trick was to use a photon of such long wavelength that it would be spread out over the entire horizon. In other words, if the horizon has Schwarzschild radius r sub s, the photon should have about the same wavelength. Even longer wavelengths might seem like an option, but they would just bounce off the black hole without getting trapped. Bekenstein suspected that an extra bit added to the black hole would make it grow by a tiny increment, similar to the way that adding an extra rubber molecule to a balloon would increase its size. But calculating the growth required a few intermediate steps. Let me outline them first. 1. To begin with, we need to know how much the energy of the black hole increases when we add a single bit of information. That amount, of course, is the energy of the photon that carries the bit. So, determining the energy of the photon is the first step. 2. Next, we need to determine how much the mass of the black hole changes when the extra bit is added. To do this, we recall Einstein's most famous equation, E equals mc squared. But we read it backward. It tells us the change in mass in terms of the added energy. Once the change in mass is known, we can compute the change in the Schwarzschild radius using the same formula that Michel, Laplace, and Schwarzschild worked out. See Chapter 2. R sub s equals 2mg divided by c squared. Finally, we must determine the increase in the area of the horizon. For that, we need the formula for the area of a sphere. Area of horizon equals 4 pi r sub s squared. We begin with the energy of the one-bit photon. As I explained earlier, the photon should have a long enough wavelength that its location is uncertain within the black hole. That means the wavelength should be r sub s. According to Einstein, a photon of wavelength r sub s has an energy, E, given by the following formula. E equals hc divided by r sub s. In this formula, h is Planck's constant, and c is the speed of light. The implication is that dropping a single bit of information into the black hole will increase its energy by an amount hc divided by r sub s. The next step is to compute how much the mass of the black hole changes. To convert energy to mass, you have to divide by c squared, which means that the mass of the black hole will increase by an amount h divided by r sub s, c. Change in mass equals h divided by r sub s, c. Let's plug in some numbers to see how much a single bit would add to the mass of a solar mass black hole. Planck's constant, h, 6.6 times 10 to the negative 34th power. Schwarzschild radius of black hole r sub s, 3,000 meters, equals 2 miles. Speed of light, c, 3 times 10 to the 8th power. Newton's constant, g, 6.7 times 10 to the negative 11th power. Thus, one bit of information added to a solar mass black hole will add an astoundingly small amount of mass. Increase in mass equals 10 to the negative 45th power kilograms. But still, as they say, that ain't nothing. Let's proceed to step 3, using the connection between mass and radius to calculate the change in r sub s. In algebraic symbols, the answer is as follows. Increase in r sub s equals 2hg divided by r sub s c cubed. For the solar mass black hole, r sub s is about 3,000 meters. If we plug in all the numbers, we will find that the radius will increase by 10 to the negative 72nd power meters. This is not only vastly smaller than a proton, but it is also vastly smaller than the Planck length, 10 to the negative 35th power meters. With such a small change, you might wonder why we even bother to calculate it. But it would be a mistake to ignore it. The final step is figuring out how much the area of the horizon will change. For the solar mass black hole, the increase in the horizon area is about 10 to the negative 70th power square meters. That's very small, but again, that ain't nothing. And not only ain't it nothing, it's something very special. 10 to the negative 70th power square meters just happens to be 1 square Planck unit. Is that an accident? What would happen if we tried it for an Earth mass black hole, a black hole as big as a cranberry, or a black hole 1 billion times more massive than the Sun? Try it out, either with numbers or with equations. Whatever the size of the original black hole, this is the rule. Adding 1 bit of information will increase the area of the horizon of any black hole by 1 Planck unit of area, or 1 square Planck unit. Somehow, hidden in the principles of quantum mechanics and the general theory of relativity, there is a mysterious connection between indivisible bits of information and Planck-sized bits of area. When I explained all of this to my pre-med physics class at Stanford, someone in the back of the room let out a long, low whistle, then said, "Cool." It is cool, but it's also profound and probably holds the key to the puzzle of quantum gravity. Now imagine building up the black hole bit by bit, just as you might fill a bathtub atom by atom. Each time you add a bit of information, the area of the horizon increases by 1 Planck unit. By the time the black hole is completed, the area of the horizon will be equal to the total number of bits of information hidden in the black hole. That was Bekenstein's great achievement, all summarized in this slogan. The entropy of a black hole measured in bits is proportional to the area of its horizon measured in Planck units. Or more succinctly, information equals area. It almost seems that the horizon is densely covered with incompressible bits of information, more or less the same way that a tabletop could be densely covered with coins. Adding an extra coin to the crowd would increase its area by the area of 1 coin. Bits, coins, it's the same principle. The only problem with this picture is that there are no coins at the horizon. If there were, Alice would have discovered them when she fell into the black hole. According to the general theory of relativity, to the freely falling Alice, the horizon is an invisible point of no return. The possibility that she will encounter anything like a table full of coins is in direct conflict with Einstein's equivalence principle. This tension, the apparent inconsistency between the horizon as a surface, packed densely with material bits, and the horizon as a mere point of no return, was the casus belli of the black hole war. Another point has puzzled physicists since Bekenstein's discovery. Why is the entropy proportional to the area of the horizon and not the volume of the interior of the black hole? It seems as if there is a lot of wasted space inside. In fact, a black hole sounds an awful lot like Ptolemy's library. We will return to that point in Chapter 18, where we will see that all the world is a hologram. Although Bekenstein had the right idea, black hole entropy is indeed proportional to area. His argument was not perfectly precise, and he knew it. He didn't say that entropy is equal to the area measured in Planck units. Because of a number of uncertainties in his calculation, all he could say was that the entropy of a black hole is about equal, or proportional, to the area. In physics, about is a pretty slippery word. Is it twice the area, or a quarter of the area? Bekenstein's arguments, though brilliant, were not powerful enough to fix the exact factor of proportionality. In the next chapter, we will see how Bekenstein's discovery of black hole entropy led Stephen Hawking to his greatest insight. Black holes not only have entropy, as Bekenstein correctly surmised, but they also have temperature. They are not the infinitely cold, dead objects that physicists had thought them to be. Black holes glow with an inner warmth, but in the end that warmth leads to their destruction. Chapter 9. Black Light. The winter wind is meanest in big cities. It funnels down long corridors between flat-faced buildings and whips around corners, mercilessly flailing unfortunate pedestrians. One very nasty day in 1974, I was out taking a long run through the icy streets of northern Manhattan, icicles of sweat hanging from my long hair. After 15 miles, I had reached exhaustion, but I was still a regrettable 2 miles from my warm office. Without my wallet, I didn't even have the necessary 20 cents to take the subway back. But luck was with me. As I stepped off the curb somewhere around Dyckman Street, a car pulled up next to me, and Åge Petersen stuck his head out the window. Åge was a delightful pixie of a Dane who had been Niels Bohr's assistant in Copenhagen before coming to the United States. He loved quantum mechanics and lived and breathed Bohr's philosophy. Once inside the car, Åge asked if I was on my way to Dennis Sharma's lecture at the Belfer School. I wasn't. In fact, I didn't know anything about Sharma or his lecture. Instead, I was thinking about a hot bowl of soup in the university cafeteria. Åge had met Sharma in England and said that he was an enormously amusing Englishman from Cambridge University who could be counted on for lots of good jokes. Åge thought that the lecture had something to do with black holes, some work that Sharma's student had done and that had Cambridge all abuzz. I promised Åge that I would show up. The Yeshiva University cafeteria was not a place much to my liking. The food was not bad. The soup was kosher, that I couldn't have cared less about, and it was hot, that was important. But the conversation among the students irritated me. It was almost always about the law, not the federal law, or the state or city law, or the laws of science. Rather the hair-splitting minutiae of Talmudic law that animated the young yeshiva undergraduates. Would Pepsi be kosher if it were made in a factory that was built on a former pig farm? What if the ground was covered with plywood before the factory was built? That kind of thing. But the hot soup and cold weather encouraged me to dawdle and eavesdrop on some students at the next table. This time, the subject of the conversation was an item that even I cared about: toilet paper. The raging Talmudic debate was over the momentous issue of whether toilet paper rollers may be restocked during the Sabbath, or whether one must use the paper straight from an unmounted roll. From various passages in Rabbi Akiva's writings, one faction had surmised that the great man would have insisted on rigorous obedience to certain laws which forbade restocking the roller. The other faction believed that the incomparable Rambam had made very clear in the Guide for the Perplexed that certain necessary tasks were exempt from these Talmudic injunctions. Rambam is the nickname of Rabbi Moses ben Maimon, who is better known to the non-Jewish world as Maimonides. And logical analysis favored the view that toilet paper restocking was one of those tasks. After half an hour, the argument was still raging. Several new young rabbis-to-be had joined the fray with additional ingenious, almost mathematical arguments, and I finally tired of the debate. You may wonder what this has to do with the subject of this book, Black Holes. Only this. My dalliance in the cafeteria caused me to miss the first 40 minutes of Dennis Sharma's brilliant lecture. Cambridge University, where Sharma was professor of astronomy and cosmology, was one of 3 places, besides Princeton and Moscow. The Great Gravity Center in Moscow was led by the legendary Russian astrophysicist and cosmologist Yakov B. Zeldovich, where the brightest and the best were testing their intellects against the profound puzzles of gravity. And as at Princeton, its young intellectual warriors were led by a charismatic, inspirational leader. Sharma's boys were a stellar group of brilliant young physicists, including Brandon Carter, formulator of the anthropic principle in cosmology, Sir Martin Rees, the Astronomer Royal of Great Britain, who now occupies Sir Edmund Halley's chair, Halley of cometary fame, Philip Candelas, the current Rouse Ball Professor of Mathematics at Oxford, David Deutsch, one of the inventors of quantum computing, John Barrow, a distinguished Cambridge astronomer, and George Ellis, the well-known cosmologist. Oh, yes, and there was also Stephen Hawking, who now sits in Isaac Newton's chair at Cambridge. It was, in fact, Stephen's work that Dennis was reporting that frigid day in 1974, but at the time, the name Stephen Hawking meant nothing to me. By the time I arrived at Sharma's lecture, it was 2/3 over. I was immediately sorry that I hadn't gotten there earlier. For one thing, I was not looking forward to going out into the freezing sleet in my running outfit again. It had gotten dark and no doubt even colder by the time Dennis finished. But it was more than the fear of frostbite that made me wish that Sharma was just beginning. As Aga had said, Dennis was an enormously entertaining speaker. The jokes were indeed outstanding, but more to the point, I was fascinated by the single equation on the blackboard. Usually by the end of a theoretical physics lecture, the blackboard is filled with mathematical symbols. But Sharma was a man of few equations. When I arrived, the blackboard looked about like this. At the top there was a circle with rays emanating from it, and underneath an equation, T equals hc cubed over 16 pi squared gmk. Within 5 minutes I had deciphered what the symbols represented. In fact, they were all standard notation for familiar quantities in physics. But I didn't know the context, what the formula described, although I could tell that it was either very deep or very silly. It had only the most fundamental constants of nature in it. Newton's constant, g, which governs the force of gravity, was in the denominator, an odd place to find it. C, the speed of light, indicated that the special theory of relativity was involved. Planck's constant, h, whispered quantum mechanics. And then there was K, Boltzmann's constant. It was the last that seemed so out of place. What the hell was it doing there? Boltzmann's constant has to do with heat and the microscopic origin of entropy. What were heat and entropy doing in a quantum gravity formula? And what about the number 16 and pi squared? These were the kind of mathematical numbers that appear in all sorts of equations. No hint there. M was familiar, and Sharma's words reinforced my impression of its meaning. M was mass. Within a couple of minutes, I could tell that it was the mass of a black hole. Okay, black holes, gravity, and relativity, that made sense, but adding quantum mechanics seemed odd. Black holes are enormously heavy as the stars that preceded them, but quantum mechanics is for small things, atoms, electrons, and photons. Why bring quantum mechanics into a discussion of something as heavy as a star? Most confusing, the left side of the equation represented temperature, T. The temperature of what? The last 15 or 20 minutes of Sharma's lecture were enough for me to put the pieces together. One of Dennis's students had discovered something very odd. Quantum mechanics gives black holes thermal property, heat, and along with heat comes temperature. The equation on the blackboard was a formula for the temperature of a black hole. How strange, I thought. What gave Sharma the daffy idea that a dead star, a star that had completely run out of fuel, would have a temperature other than absolute zero? Looking at the intriguing formula, I saw an interesting correlation. The temperature of a black hole would be inverse to its mass. The bigger the mass, the smaller the temperature. A huge astronomical black hole as large as a star would have a tiny temperature, much colder than any object in any laboratory on Earth. But the real surprise which made me sit up in my chair was that tiny black holes, if they existed, were extraordinarily hot, hotter than anything we had ever imagined. Yet Sharma had an even bigger surprise. Black holes evaporate. Physicists till then had believed that black holes, like diamonds, were forever. Once formed, no mechanism known to physical science could destroy or eliminate a black hole. The black vacancy in space formed by a dead star would persist, infinitely cold, infinitely silent, for all eternity. But Sharma told us that, like a drop of water left out in the sun, little by little, black holes evaporate and eventually disappear. As he explained, electromagnetic heat radiation carries away the mass of a black hole. To explain why Dennis and his student thought this, I need to fill you in on some things about heat and heat radiation. I'll come back to black holes, but first, a digression. Heat and temperature. Heat and temperature are among the most familiar concepts in physics. We all have a built-in thermometer and a built-in thermostat. Evolution provided us with a hardwired sense of cold and warmth. Warmth is heat, and cold is its absence. But what exactly is this stuff called heat? What goes on in a bathtub of hot water that's absent when the bathwater gets cold? If you look carefully through a microscope at little tiny specks of dust or grains of pollen suspended in warm water, you will see the grains stagger around like drunken sailors. The hotter the water, the more agitated the grains appear. It was Albert Einstein who in 1905 first explained that this Brownian motion is caused by the grains being constantly bombarded by rapidly moving, energetic molecules. Water, like all other materials, is composed of molecules moving hither and thither, banging into one another, into the walls of the container, and into any foreign impurities. When that motion is random and chaotic, we call it heat. For ordinary objects, when you add energy in the form of heat, the result is an increase in the random kinetic energies of the molecules. Temperature is, of course, related to heat. When the zigzagging molecules hit your skin, they excite nerve endings, and you experience a sense of temperature. The larger the energy of the individual molecules, the more your nerve endings are affected, and the hotter you feel. Your skin is just one of the many types of thermometers that can sense and register the chaotic motion of molecules. So, roughly speaking, the temperature of an object is a measure of the energy of its individual molecules. When an object cools, energy is being drained away, and the molecules are slowing down. Eventually, as more and more energy is eliminated, the molecules reach the lowest possible energy state. If we could ignore quantum mechanics, this would happen when the molecular motion ceased altogether. At that point, there would be no more energy to drain away, and the object would be at absolute zero. The temperature cannot be lowered any further than that. Black holes are black bodies. Most objects reflect at least a little bit of light. The reason that red paint is red is that it reflects red light. More accurately, it reflects a certain combination of wavelengths that the eye and brain perceive as red. Similarly, blue paint reflects a combination that we perceive as blue. Snow is white because the surface of ice crystals reflects all the visible colors equally. The only difference between snow and a mirror-like sheet of ice is that the granular structure of the snow scatters the light in all directions and breaks up the reflected image into thousands of tiny fragments. But some surfaces reflect almost no light at all. Any light that falls on the sooty surface of a blackened pot is absorbed into the layer of soot, heating both the black exterior and eventually the iron itself. These are the objects that our brains perceive as black. The physicist's term for a totally light-absorbing object is black body. By the time Sharma lectured at my university in New York, physicists had long known that black holes are black bodies. Laplace and Michel had suspected it in the 18th century, and Schwarzschild's solution of Einstein's equations had proved it. Light, falling onto the horizon of a black hole, is completely absorbed. Black hole horizons are the blackest of the black. But what no one knew before Hawking's discovery was that black holes have a temperature. Before that, if you had asked a physicist, what is the temperature of a black hole, the initial response probably would have been, black holes don't have temperatures. You might have responded, nonsense, everything has a temperature. A little thought might then have provoked the answer, okay, a black hole has no heat, so it must be at absolute zero, the lowest possible temperature. In fact, before Hawking, all physicists would have claimed that black holes were indeed black bodies, but black bodies at absolute zero. Now, it's not correct to say that black bodies don't give off any light at all. Take a sooty pot and heat it to a few hundred degrees and it will glow red, even hotter, and it will glow orange, then yellow, and eventually it will have a bright bluish-white appearance. Curiously, according to the physicist's definition, the sun is a black body. How odd, you say. The sun is about as far from being black as anything you can imagine. Indeed, the sun's surface radiates plenty of light, but it reflects none. To a physicist, that makes it a black body. Cool the hot pot, and it will glow with invisible infrared radiation. Even the coldest objects radiate some electromagnetic radiation, as long as they are not at absolute zero. But the radiation emitted by black bodies is not reflected light. It is produced by vibrating or colliding atoms, and unlike reflected light, the color depends on the temperature of the body. What Dennis Sharma explained was remarkable, and seemed a bit crazy at the time. He said that black holes are black bodies, but they are not at absolute zero. Every black hole has a temperature that depends on its mass. The formula was on the blackboard. He told us one more thing, in some way the most surprising of all. Since a black hole has heat and temperature, it must radiate electromagnetic radiation, photons, in the same way that a hot black pot does. That means that it loses energy. According to Einstein's E equals mc squared, energy and mass are really the same thing, so if a black hole loses energy, it also loses mass. That brings us to the punchline of Sharma's story. The size of a black hole, the radius of its horizon, is directly proportional to its mass. If the mass decreases, it follows that the size of the black hole decreases. So as a black hole radiates energy, it shrinks until it is no bigger than an elementary particle, and then it is gone. According to Sharma, black holes evaporate away like puddles on a summer day. Throughout the lecture, or at least the part I witnessed, Sharma made it very clear that he was not the source of these discoveries. It was, Stephen says this, and Stephen says that. But despite what Dennis said, my impression at the end of the lecture was that the unknown Stephen Hawking was just a lucky student who happened to be at the right place at the right time to hook up with Dennis's research project. It is conventional for a well-known physicist to generously mention the name of a bright student during a lecture. Whether the ideas were brilliant or crackpot, I naturally assumed that they originated with the more senior physicist. That evening I was firmly disabused of this assumption. Age, a few other physics faculty members from Belfer, and I took Dennis to dinner at a fine Italian restaurant in Little Italy. Over the meal, Dennis told us all about his remarkable student. In fact, Stephen was not a student at all. When Dennis spoke of his student Hawking, he was speaking in the same way that the proud father of a Nobel Prize winner might speak of my boy. By 1974, Stephen was a rising star in the world of general relativity. He and Roger Penrose had made major contributions to the subject. It was my own ignorance that had led me to believe that Stephen was merely the student of a generous thesis advisor. Over Italian food and good wine, I heard the amazing, stranger-than-fiction tale of the young genius who had blossomed only after being diagnosed with a debilitating disease. As a bright but somewhat egotistical graduate student, Stephen contracted Lou Gehrig's disease. The progression of the disease had been rapid, and he was, at the time of the dinner, almost completely paralyzed. Though unable to write equations and barely able to communicate, Stephen was holding his medical nemesis at bay and at the same time exploding with brilliant ideas. The prognosis was grim. Lou Gehrig's disease is a brutal killer, and Stephen would, by all accounts, be dead in a couple of years. Meanwhile, he was having a ball, joyously, Sharma's word, revolutionizing physics. At that time, Dennis's description of Stephen's courage under adversity seemed an exaggeration, but after knowing Stephen for almost 25 years, I would say that it sounded just like him. Both Stephen and Sharma were unknown quantities to me, and I had no idea whether evaporating black holes were a tall tale, a wild fringe speculation, or genuine. It was possible that I had missed some important parts of the argument while being educated about Jewish toilet paper laws. More likely, Dennis had just reported Stephen's conclusion without providing any technical underpinning. After all, Sharma was not an expert on the advanced methods of quantum field theory that Hawking had used. As I said earlier, he was a man of few equations. In retrospect, it seems odd that I didn't connect Sharma's lecture with the brief conversation I'd had 2 years earlier with Richard Feynman at the West End Cafe. Feynman and I also were speculating about how black holes might eventually disintegrate. But many months would pass before I put the two together. Stephen's argument. By his own account, Stephen did not at first believe the strange conclusion that Jacob Bekenstein, the then unknown Princeton student, had come to. How could black holes have entropy? Entropy is associated with ignorance of hidden microscopic structure, such as our ignorance of the precise location of the water molecules in a bathtub of warm water. Einstein's theory of gravity and Schwarzschild's black hole solution have nothing to do with microscopic entities. Moreover, it seemed that there was nothing about a black hole to be ignorant of. Schwarzschild's solution of Einstein's equations was unique and precise. For each value of mass and angular momentum, there was one and only one black hole solution. That's what John Wheeler meant when he said black holes have no hair. By the usual logic, a unique configuration, recall the perfect BMW of Chapter 7, should have no entropy. Bekenstein's entropy made no sense to Hawking until he found his own way to think about it. The key for Hawking was temperature, not entropy. By itself, the existence of entropy doesn't imply that a system has temperature. Logically, it is possible to imagine systems that can be arranged in many ways without changing their energy, but this never happens in real-world situations. A third quantity, energy, also comes into the equation. The connection between energy, entropy, and temperature goes back to the origin of thermodynamics in the early 19th century. Thermodynamics is the study of heat. Steam engines were the thing then, and the Frenchman Nicolas Leonard Sadi Carnot was what you might call a steam engineer. He was interested in a very practical question: how to use the heat contained in a given amount of steam to do useful work in the most efficient way, how to get the biggest bang for the buck. In this case, useful work might mean accelerating a locomotive, which would require converting heat energy into the kinetic energy of a large mass of iron. Heat energy means the disorganized, chaotic energy of random molecular motion. By contrast, the kinetic energy of a locomotive is organized into the simultaneous, synchronized motion of a huge number of molecules all moving together. So the problem was how to turn a given amount of disorganized energy into organized energy. The problem was that no one really understood exactly what organized and disorganized energy meant. Carnot was the first to define entropy as a measure of disorganization. My own introduction to entropy was as an undergraduate mechanical engineering student. Neither I nor any of the other students knew anything about the molecular theory of heat, and I would bet that the professor didn't either. The course, Mechanical Engineering 101, Thermodynamics for Mechanical Engineers, was so confusing that I, who was by far the best student in the class, couldn't make any sense of it. Worst of all was the concept of entropy. We were told that if you heat something a small amount, the change in thermal energy divided by the temperature is the change in entropy. Everyone copied it down, but no one understood what it meant. It was as incomprehensible to me as the change in the number of sausages divided by the onionization is called the Flugelweiss. Part of the problem was that I really didn't understand temperature. According to my professor, temperature is what you measure with a thermometer. Yes, I might have asked, but what is it? I am fairly sure the answer would have been, I told you, it's what you measure with a thermometer. Defining entropy in terms of temperature is putting the cart before the horse. Although it's true that we all have an innate sense of temperature, the more abstract concepts of energy and entropy are much more basic. The professor should have first explained that entropy is a measure of hidden information and is given in bits. Then he could have gone on to say, correctly, temperature is the increase in the energy of a system when you add 1 bit of entropy. Strictly speaking, it's the temperature, measured from absolute zero, times Boltzmann's constant. Boltzmann's constant is nothing but a conversion factor that physicists often set to 1 by choosing convenient units for temperature. The energy change when you add 1 bit? That's exactly what Bekenstein had figured out for a black hole. Apparently, Bekenstein had calculated the temperature of a black hole without realizing it. Hawking immediately saw what Bekenstein had missed. But the idea that a black hole has a temperature seemed so absurd to Stephen that his first reaction was to dismiss the whole thing as nonsense, entropy along with temperature. Perhaps part of the reason he reacted this way was that the evaporation of a black hole seemed so ridiculous. I don't know exactly what made Stephen rethink things, but he did. Using the sophisticated mathematics of quantum field theory, he found his own way to prove that black holes radiate energy. The term quantum field theory reflects the confusion that was left in the wake of Einstein's discovery of photons. On the one hand, Maxwell had convincingly proved that light is a wave-like disturbance of the electromagnetic field. He and others had thought of space as something that can vibrate, almost like a bowl of jello. This hypothetical jello is called the luminiferous ether, and like jello, when it is disturbed by a vibration, in the case of jello, touching it with a vibrating tuning fork would work, waves spread out from the disturbance. Maxwell envisioned oscillating electric charges disturbing the ether and radiating light waves. Einstein's photons confused things for more than 20 years, until Paul Dirac eventually applied the powerful mathematics of quantum mechanics to the wave-like vibrations of the electromagnetic field. The most important consequence of quantum field theory for Hawking was the idea that the electromagnetic field has the quantum jitters, see Chapter 4, even if no vibrating charges are disturbing it. In empty space, the electromagnetic field shimmers and vibrates with vacuum fluctuations. Why don't we feel the vibrations of empty space? It's not because they are very gentle. In fact, the vibrations of the electromagnetic field in a small region of space are exceedingly violent. But because empty space has less energy than anything else, there is no way for the energy in the vacuum fluctuations to be transferred to our bodies. There is another kind of jitteriness in nature that is very noticeable: thermal jitters. What is the difference between a pot of cold water and a pot of hot water? The temperature, you say. But that's just a way of saying that the hot water feels hot and the cold water feels cold. The real difference is that the hot water has more energy and more entropy. The pot is full of chaotic, randomly moving molecules that are far too complicated to keep track of. This motion has nothing to do with quantum mechanics, and it is not subtle. Stick your finger in the pot and you'll have no trouble detecting thermal fluctuations. The jittery thermal motion of individual molecules can't be seen because water molecules are too small. But the immediate effect of the thermal jitters is not hard to detect. As I mentioned earlier, grains of pollen suspended in a glass of warm water will move with random, jittery Brownian motion, which has nothing to do with quantum mechanics. It is due to the heat in the water, which causes the water molecules to randomly bombard the grains. When you put your finger in the glass, the same random bombardment on your skin excites the nerve endings and makes the water feel warm. Your skin and nerves absorb a bit of energy from the surrounding heat. Even in the absence of water, air, or any other substance, heat-sensitive nerves can be excited by the thermal vibrations of black-body radiation. In this case, the nerves absorb heat from the surroundings by absorbing photons. But this is possible only if the temperature is above absolute zero. At absolute zero, the quantum jitters of the electric and magnetic field are more subtle and don't have the same obvious effects. The two kinds of jitters, thermal and quantum, are very different, and under ordinary conditions don't get mixed up with each other. Quantum fluctuations are an irreducible part of a vacuum and can't be eliminated, while thermal fluctuations are due to excess energy. The subtleties of quantum fluctuations, why we can't feel them and how they differ from thermal fluctuations, are on the edge of explainability in a book trying to avoid complex mathematics, and any analogy or picture that I use will have its logical defects. But some explanation is necessary if you are to grasp what was at stake in the Black Hole War. Just remember Feynman's caveat about explaining quantum phenomena. Quantum field theory suggests a way of visualizing the two kinds of fluctuations. Thermal fluctuations are due to the presence of real photons, photons that bombard our skin and transfer energy to it. Quantum fluctuations are due to virtual photon pairs, which are created, then quickly absorbed back into the vacuum. There is a Feynman diagram of space-time, time vertical and space horizontal, with both real photons and virtual photon pairs. The real photons are unending dashed world lines. Their presence indicates heat and thermal jitters. But if space were at absolute zero, there would be no real photons. Only the microscopic loops of virtual photons, rapidly flashing into and out of existence, would remain. The virtual photon pairs are part of the vacuum, what we usually think of as empty space, even when the temperature is at absolute zero. Under ordinary conditions, there is no confusion between the two kinds of jitters. But a black hole horizon is not ordinary. Near the horizon, the two kinds of fluctuations become confused in a way that no one ever expected. To get some idea of how it happens, imagine Alice freely falling into the black hole in an environment of absolute zero temperature, a perfect vacuum. She is surrounded by virtual photon pairs, but she doesn't notice them. There are no real photons in her vicinity. Now consider Bob, who hovers above the horizon. For him, things are more confusing. Some of the virtual photon pairs, the ones that Alice doesn't notice, may be partly inside the horizon and partly outside. But a particle behind the horizon is irrelevant to Bob. Bob sees a single photon and has no way of recognizing that it belongs to a virtual pair. Believe it or not, such a photon stranded on the outside while its partner is behind the horizon will affect Bob and his skin exactly as if it were a real thermal photon. Near the horizon, the separation into thermal and quantum depends on the observer. What Alice detects or doesn't detect as quantum jitters, Bob detects as thermal energy. Thermal and quantum fluctuations become two sides of the same coin in regard to a black hole. We will come back to this point in Chapter 20 when we learn about Alice's airplane. Using the mathematics of quantum field theory, Hawking calculated that the disturbance of the vacuum fluctuations due to a black hole causes photons to be emitted, exactly as if the black hole horizon were a hot black body. These photons are called Hawking radiation. Most interesting, a black hole radiates as if its temperature were approximately the same as Bekenstein's argument would give, had Bekenstein made the argument. In fact, Hawking was able to go further than Bekenstein. His methods were so precise that he could calculate the exact temperature and, working backward, the entropy of the black hole. Bekenstein had claimed only that the entropy was proportional to the area of the horizon measured in Planck units. Hawking no longer needed to use the ambiguous term proportional to. According to his calculation, the entropy of a black hole is precisely 1/4 of the horizon area measured in Planck units. Incidentally, the equation that Hawking derived for the temperature of a black hole was the one on the blackboard when I walked into Dennis Sharma's lecture. T equals 1 over 16 pi squared times C cubed H over GMK. Notice that in Hawking's formula, the mass of the black hole is in the denominator. That means that the larger the mass, the colder the black hole, and conversely, the smaller the mass, the warmer the black hole. Let's try out the formula for one black hole. Here are the values of the constants. These numbers are all quoted in meters, seconds, kilograms, and degrees Kelvin. The unit of measurement on the Kelvin scale is the same as on the Celsius scale, except the temperature is measured from absolute zero instead of from the freezing point of water. Ordinary room temperature is 300 degrees Kelvin. C equals 3 times 10 to the 8th power. G equals 6.7 times 10 to the negative 11th power. H equals 7 times 10 to the negative 34th power. K equals 1.4 times 10 to the negative 23rd power. Let's take the case of a star with a mass 5 times that of the Sun that ultimately collapses to form a black hole. Its mass, in kilograms, would be m equals 10 to the 31st power. If we plug all of these numbers into Hawking's formula, we find that the temperature of the black hole is 10 to the negative 8th power degrees Kelvin. That's a very small temperature, about 10 billionths of a degree above absolute zero. Nothing in the natural world is that cold. Interstellar and even intergalactic space is much warmer than that. There are black holes of even lower temperature at the centers of galaxies, 1 billion times more massive than stellar black holes and 1 billion times bigger. They are also 1 billion times colder. But we can also contemplate much smaller black holes. Suppose some cataclysmic event crushed the Earth. The mass of the Earth is about 1 million times smaller than the mass of a star. The resulting black hole would have the stupendous temperature of about 0.01 degrees above absolute zero. Warmer than the stellar black hole, but still awfully cold. Colder than liquid helium and far colder than frozen oxygen. A black hole with the mass of the Moon would get all the way up to 1 degree Kelvin. But now consider what happens as a black hole emits Hawking radiation and evaporates. As the mass decreases and the black hole shrinks, the temperature rises. In time, the black hole will become hot. By the time it has the mass of a large boulder, its temperature will have grown to 1 billion degrees. By the time it has reached the Planck mass, its temperature will have risen to 10 to the 32nd power degrees. The only time any place in the universe might have been anywhere near that temperature was at the beginning of the Big Bang. Hawking's calculation showing how black holes evaporate was more than a brilliant tour de force. I believe that in time, when the repercussions are fully understood, physicists will recognize it as the beginning of a great scientific revolution. It's too early to know exactly how that revolution will play out, but it will touch on the deepest issues, the nature of space and time, the meaning of elementary particles, and the mysteries of the origin of the universe. Physicists incessantly question whether Hawking belongs among the greatest physicists of all time and where he ranks in the hierarchy. In response to those who doubt Hawking's greatness, I will only suggest that they go back and read his 1975 paper, Particle Production by Black Holes. Yet no matter how great he may be, on at least one occasion, Stephen Hawking lost track of his bits. And that's what started the Black Hole War. Part 2. Surprise Attack. Chapter 10. How Stephen lost his bits and didn't know where to find them. It is impossible as I state it, and therefore I must in some respect have stated it wrong. Sherlock Holmes. According to several newspaper articles, the war in Iraq has lasted longer than World War II. What the journalists really mean is that the war has lasted longer than America's involvement in World War II. That war began in the fall of 1939 and didn't end till the summer of 1945. Americans tend to forget that the war was into its third year by the time Pearl Harbor was attacked. Perhaps I am making the same self-centered mistake by saying that the Black Hole War began in 1983 in Werner Erhard's attic. Stephen's attack actually dates back to 1976, but you can't have a war without two sides. Although the attack was largely ignored, it was a direct frontal assault on one of the most trusted principles of physics, the law that says that information is never lost, or, in its short form, information conservation. Because it is so central to everything that followed, let's go over the law of information conservation once more. Information is forever. What does it mean for information to be destroyed? In classical physics, the answer is simple. Information is destroyed if the future loses track of the past. Surprisingly, this can happen even with a deterministic law. To illustrate, let's return to the three-sided coin that we played with in Chapter 4. The three faces of the coin were called H, T, and F, for heads, tails, and feet. In that chapter, I described two deterministic laws by the following diagrams. Going clockwise, H goes into T, T goes into F, F goes into H. Going counterclockwise, H goes into F, F goes into T, T goes into H. Both laws have the deterministic property that whichever state the coin is in, it is possible to say with absolute certainty both the next state and the previous state. Compare that with a law described by another diagram. H goes into T, and F goes into T, T goes into H. Or by the formula, H goes into T, T goes into H, F goes into T. In words, if the coin is heads at one instant, it will be tails at the next instant. If it is tails, it will become heads, and if it is feet, it will next be tails. This rule is completely deterministic. Wherever you begin, the future is laid out forever by the law. Suppose, for example, that we start with F. The subsequent history is completely determined. FTH, THT, HTH, T. If we start with H, the history will be HT, 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 HT. And if we start with T, it will be TH, 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 T. There's something odd about this law, but what is it exactly? Like other deterministic laws, the future is completely predictable. But when we try to determine the past, things break down. Suppose we find the coin in state H. We can be certain that the previous state was T. So far, so good. But let's try to go back another step. There are two states that lead to T, namely H and F. That presents a problem. Did we get to T from H or from F? There is no way to know. This is what it means to lose information, but it never happens in classical physics. The mathematical rules that Newton's law and Maxwell's electromagnetic theory are based on are very clear. every state is followed by a unique state, and every state is preceded by a unique state. The other way that information can be lost is if there is a degree of randomness in the law. In that case, it is obviously impossible to be certain of the future or the past. As I explained earlier, quantum mechanics has its random element, but there is also a deep sense in which information is never lost. I illustrated this for a photon in Chapter 4, but let's do it again, this time using an electron colliding with a stationary target, such as a heavy nucleus. The electron comes in from the left, moving in the horizontal direction. It collides with the nucleus and goes off in some unpredictable new direction. A good quantum theorist can calculate the probability that it will go off in a particular direction, but he cannot predict the direction with certainty. There are two ways to check whether the information regarding initial motion has been retained. Both of them involve running the electron backward with a reversed law. In the first case, an observer checks where the electron is just before reversing the law. He can do that in various ways, most of them using photons as probes. In the second case, the observer doesn't bother to check. He just reverses the law without intervening in any way with the electron. The results of the two experiments are entirely different. In the first case, after the electron is run backward, it ends up in a random location, moving in an unpredictable direction. In the second case, when no check is made, the electron always ends up reversing its motion back along the horizontal direction. When the observer looks at the electron for the first time after starting the experiment, he will find it moving exactly as it started, except in reverse. It seems that information is lost only when we actively intervene with the electron. In quantum mechanics, as long as we don't interfere with the system, the information that it carries is as indestructible as it is in classical physics. Stephen attacks. It would have been hard to find two more sullen expressions than Gerard 't Hooft's and mine in all of San Francisco that day in 1983. High above Franklin Street, in Werner Erhard's attic, war had been declared. A direct attack on our deepest beliefs. Stephen the Bold, Stephen the Daredevil, Stephen the Destroyer had all the heavy weapons, and the angelic, devilish smile showed that he knew it. In no way was the attack personal. The blitzkrieg was aimed right at the central pillar of physics, the indestructibility of information. Information is often scrambled beyond recognition, but Stephen was arguing that the bits of information that fall into a black hole are permanently lost to the outside world. On the blackboard, he had the diagram to prove it. This book is continued on Disc 5.